Hello everyone, today let's take a look at Quantipus number 81, asking us what are the number of ways 5 distinct employees can sit in 3 indistinguishable offices. So why is this a set partitions question? Well, it just comes down to this word right here, distinct employees into indistinguishable offices, right? We're putting unique objects into identical boxes, basically. And it's different than integer partitions because in integer partitions, we were dealing with identical objects going into identical boxes, but now it's distinct into identical. It's actually called set partitions because the term set kind of implies that the objects are actually distinct. So just to run through some examples, say I have my 5 employees labeled A, B, C, D, and E because they're unique now. So one example of a way to place them in these offices is we have 4 in one and 1 in the other and 0 in the third. But this partition should be counted differently than this partition, right, where we swap D and E, and now D is the one by itself, right, because now the objects are unique. So this kind of group right here, we can call this integer partition 4, 1, 0, right? Because we have 4 in this one, 1 in this one, and 0 in the other. But instead of counting this once, like we did in integer partitions, we now need to account for the distinctness of our objects. So for this specific integer partition, how many set partitions are there? So in this case, it's pretty simple to think about. I wrote out every single combination here, and basically you can think about it like we're choosing one of our elements to be solo, and then the other 4 are just going to go in the other group. So we have 5 elements. I'm choosing 1 to be solo, or I'm choosing 4 to be in the group. They're both equal to 5, we know. So for the integer partition 410, we want to count it 5 times in our answer. So now you can see how we're going to approach getting the final answer. We're going to take every single integer partition, and for each one of those, we're going to calculate the number of ways that we can permute these now unique items between these groups. So first, let's just calculate all of the integer partitions of 5 into 3 groups. We know how to do this. We have to list them all out, basically. So I can have 5, 0, 0. I can have 4, 1, 0. I could also have, let's say, 3, 2, 0. Then when we have 0 boxes empty, I could have 3, 1, 1 or 2, 2, 1. So this is it. Now let's calculate the set partitions for this 410. We already just did it up top. It's going to be 5. Now 500 is going to be pretty easy. There's obviously only one way that we could have all 5 in one group. Now let's look at 320. So an example of this would be like A, B, C, and then D, E, and then nothing here. So for this partition, what are the number of ways to uniquely group our elements? This one's also going to be pretty easy. We basically have 5 total, and we're choosing 2 to be in a pair, or you could say we're choosing 3 to be in a triplet. They're both equal to 10. So 10 ways for 320. Now let's move on to 311. It's going to get a little trickier here. So this is one possible way that 311 could look like, right? Where we have 3 here, 1 here, 1 here. So you look at this, you say, okay, I have 5 elements. I need to choose 3 to be in my triplet. So 5, choose 3. And once I've chosen my triplet, for instance, A, B, and C, well then D and E can only go into the remaining 2 in one way. That's just because the offices are treated as indistinguishable. So D and E would be the exact same as E and D, right? So the answer for this one's going to be 5, choose 3, which again is 10. Another way you could have thought about it is, okay, I have 5 choices for my first solo. Then once I've chosen that, I have 4 choices for my second solo, but the order of them relative to each other doesn't matter, obviously, so I have to divide by 2, and then I get 10, and I put the remaining 3 in here, and there's only one way to do that. Okay, now let's just move on to solve 221, our final partition. So what would that look like? For instance, I could have A, B in one, and then I could have C, E in the other, and then D here. That's a possible example because I have 2, 2, 1. So how can we look at this one? Well, for our first one, we have 5 elements, and I'm choosing 2 of them to be in one of my doubles. Once I've done that, I'm going to have 3 elements remaining, and I need to choose 2 more to be in my second double. Once I've done that, I'm just going to have 1 remaining left to place in my last one, so there's just going to be one way to do that, obviously. So is this our final answer? Well, it turns out it's actually not because we're overcounting here. And we're overcounting here because the number of people in these is actually going to be the same. So for instance, if I choose A, B first, and then I have C, E for my second one, well, that's just going to be the exact same. It should be counted the same as if I chose C, E for the first one, and then A, B for the second one. So for each combo like this, I'm overcounting by a factor of 2, so I just need to divide this by 2. So 5 choose 2 is 10, 3 choose 2 is 3, so when we multiply those, we get 30, and then divide by 2, we get 15, so this is going to be 15 here. Now, one more way to think about it. Okay, I have a unique element here, so I have 5 ways to choose that. Once I've done that, I have 4 elements remaining. I need to group 2 of them together, so 4 choose 2. And then I just place the remaining 2 in the final office. 4 choose 2 is 6, and in this case, when I chose D to be my solo, then I have these ways of grouping two elements together. And then that would force the other two into the remaining office. As you can see, I drew those over here. But again, the offices are indistinguishable. You can see the overcounting here. For instance, I have A, B, C, E, these combos twice. So again, we have to divide by 2. So we're going to have 5 times 4 choose 2 divided by 2, which is also equal to 15. So there's a bunch of different ways to think about it, but you get the idea. So now all that's left to do is just count all of these up, add them all together, and when you do that, you get 41. So again, we listed out all the integer partitions, and for each integer partition, we figured out the number of ways to distribute these unique elements within that partition, and then we summed them up to get our final answer of 41. Now there's also another way of solving this using Stirling numbers, which we haven't talked about yet, and we will probably go on to solve a problem like this using Stirling numbers explicitly. But if you were to calculate it using Stirling numbers of the second kind, you would see that this is basically S53 here. This is going to be the number of ways for S52, and then this will be the number of ways for S51. So when we do that, you'll see that S53 is actually equal to 25 when we sum those up, S52 is equal to 15, and S51 is equal to 1.